Hello, everyone, and welcome to today's webinar on phosphorus pollution control, Insights into Phoslock Applications, organized by Smart Water Magazine in collaboration with Phoslock Environmental Technologies. My name is Cristina Novo, and I am technical editor at Smart Water Magazine. Today, we're going to discuss nutrient pollution, a complex global problem that can cause undesirable changes to aquatic systems. Although it is a natural phenomenon, human activity accelerates the rate at which nutrients like phosphorus enter freshwater. Even after successful catchment management, phosphorus can be retained within water bodies and cycled from the bed sediments to the overlaying waters through internal loading. This way, continued poor water quality can delay recovery for potentially decades, leading to the deterioration of lake structure and function, and ultimately to biodiversity loss. Based in Australia, Phoslock Environmental Technologies offers water treatment and remediation solutions to address excess nutrients in water bodies. Their flagship product, Phoslock, was originally developed by the Australian National Science Agency, the CSIRO, more than 20 years ago. Phoslock is an in-lake remediation solution made of lanthanum-modified bentonite. It is used to aid quicker recovery times in lakes that are affected by internal loading by reducing the concentration of phosphorus in the water column and reducing the amount of phosphorus that is released from lakebed sediments. In today's webinar, we're going to hear from two experts from Phoslock Environmental Technologies about nutrient management in freshwater bodies, how Phoslock works, application techniques, and the ecotoxicological profile of this solution. We will also hear about whole lake applications from different countries, showing the versatility, the effectiveness, the longevity, and the wider ecological benefits of using Phoslock in comparison with other in-lake measures. The webinar has attracted a lot of attention with more than 300 people registered so far. At the end, we're going to have a question and answer session. So we ask you to please send us your question using the Q&A module in Zoom. It will open a chat window. You can send them throughout the webinar and we'll address them at the end. Please identify yourself and your organization when you ask your question. The webinar is going to last about 45 minutes in total. And now I would like to introduce our speakers. Our first speaker will be Damian Whelan, General Manager for Europe, including the UK, at Phoslock Environmental Technologies. He joined the company in 2021 and has more than 26 years of experience within the utilities sector in the UK and internationally, covering municipal and non-municipal markets and including environmental and water conservation challenges. He has a strong managerial background, having held senior positions at several water engineering services and water technology companies. Damian is based in the UK. Our second speaker will be Dr. Kate Waters-Hart, Aquatic Science General Manager. She joined Phoslock Environmental Technologies in 2019 as freshwater aquatic ecologist and was appointed Aquatic Science General Manager in January 2022. This is a critical role for the business globally, where she oversees and coordinates all the science behind the company's products, applications, and data management. Kate has researched and worked on the product Phoslock for 8 years. Her PhD research investigated the recovery of aquatic macrophytes following Phoslock applications and covered whole lake applications and lab experiments. Kate is based in Scotland. Welcome, Damian and Kate. And now it's over to you for your presentation. Please, Damian, go ahead.
Thank you. Good afternoon and also good morning. From a quick glance at the attendee list, I can see that we have global participation. North, Central and South America, South Africa, India, Australia, and both here in the UK and across Europe. Welcome to you all. Before we start, I thought it'd be good for those joining who are not familiar with PET and for those watching the recording to share a few slides as a high-level company overview. So who are Phoslock Water Environmental Technologies and what do we do? We are an Australian company headquartered in Melbourne, helping to solve global water quality problems, addressing growing environmental, economic, and human health challenges. We've been doing this successfully for over 20 years with our proprietary technology Phoslock, originally developed by the Commonwealth Scientific Industrial Research Organisation, CSIRO. Operating on a global scale, we are supported by 37 full-time staff, numerous licensees, agents, and key distribution partners. Some of you on this call today may want to support or join that growing list. Supported by independent reviews, PET has distinctive advantages over competitive treatments. We are a global leader in the treatment and remediation of waters impacted by excessive levels of phosphorus, and to date have done in excess of 300 applications. All water, no matter where located, is connected. It's important to also have an operating platform that allows our technology and expertise to be utilised and for us to be just as connected with our clients. No matter where your water body is geographically, PET has the breadth, depth and expertise to fully support you. As mentioned, we have successfully completed over 300 applications globally. Looking at the list of attendees here today, I have high hopes that we can add more lakes and water bodies from more countries to this growing list of achievements and help further remediate water bodies for the benefits of everyone and everything. Water is one of our, if not most precious resources after all. Standards, approvals, and certifications are vitally important. They ensure safety, quality, reliability, and client confidence, protecting not only our health, but the health of the environment. Through these standards, scientific research and independent peer reviews enables PET to undertake multiple applications to lakes, reservoirs, and water bodies, including those identified as sites of special scientific interest, special areas of conservation, and those that fall under the Water Framework Directive. Strong, independent, and scientific validation is a key requirement for not only our clients, but government and regulatory authorities. It allows for projects to be approved, permits authorised, and reduce requests for repeat trials and studies, given the depth, quality, and focus of the research undertaken on our proprietary technology. Examples of these studies shown here confirm that Phoslock rapidly and significantly decreased total and free reactive phosphorus in the water column and shifted potentially releasable sediment-bound phosphorus fractions to residual forms after treatment. Again, the results showed a sharp reduction in the P concentrations along the water column and after the Phoslock application. And from January onwards, the settled Phoslock controlled the P release from the sediments, preventing a sharp increase in the P concentrations. These are great examples of the research showing the efficacy, performance, and positive environmental impacts of Phoslock. Today, this webinar is to provide details, case studies, and the science around that. And on that note, I will hand over to my colleague, Dr. Kate Waters-Hart, to lead the technical discussion of this phosphorus pollution control insights into Phoslock applications.
So I'm going to cover some of the technical background to Phoslock. I'm going to look over some case studies, as Damian mentioned, from different countries, looking at different lake types. And then I'm going to briefly talk about the ecotoxicity profile of Phoslock. Okay, so global phosphorus pollution is happening everywhere. You can see from the map there where anthropogenic phosphorus pollution loads are heavily based. Unfortunately, phosphorus concentrations lead to changes in the structure and function of water bodies, which ultimately leads to biodiversity loss and loss of ecosystem services. And phosphorus emissions are unfortunately set to increase thanks to climate change patterns, but also population increase. And phosphorus emissions from the agricultural sector are predicted to double by 2050. And losses from wastewater sector is also set to increase globally by 70% by 2050. So nutrient pollution management is very costly. For England and Wales, water resources are valued at more than £40 billion. And in the US, management costs are more than 2.2 billion a year. And that is quite an old figure, so that would be increased a lot more by now. By 2080, we're expected to see losses by more than 400 million alone, thanks to climate warming in the UK. And as a consequence of phosphorus pollution, there's many directives that have been set up nationally all across the globe that are trying to safeguard freshwaters, but also trying to improve them. One of them is the Water Framework Directive in Europe, in the UK. But unfortunately, 40% of lakes, even under the remit of the Water Framework Directive, are failing ecological quality targets. And more than 83% of freshwater habitats in the European Union is classed as unfavourable. And the Environment Agency in England have stated that majority of cases that fail under these targets are because of phosphorus pollution. So even if we reduce catchment phosphorus entering our lakes, they may take a really long time to recover, or they actually might not at all due to a process called internal loading or legacy phosphorus, which is where phosphorus has entered the water body through years of catchment runoff and sedimentation, and the phosphorus can be retained within the lake bed sediments and then can be cycled from the bed sediments to the overlying water column during natural lake conditions. This phosphate can then be utilised by algae and aquatic plants, and then once they die off, the phosphate then returns to the sediment, and then the cycle continues. So you'd need to switch off this internal cycling to see improvements in the water quality. So there are a number of different measures that can be used to do this. There are biological measures, such as large-scale fish removal. Typically benthic fish removal, as benthic fish through their foraging can disturb bed sediments, which can then suspend the sediments into the water column and release phosphorus. So by removing at least 70% of the population, you can reduce that. But obviously that's a continued management practice that you would need to do. There are other biological measures such as active transplantation of aquatic plants. However, this would need the chemistry of the water body to have been in a favourable status. So you would need to reduce the phosphorus concentrations in the water body to have those macrophytes continually growing and benefiting the feedback mechanisms that they provide through stabilising bed sediments, for example. There's physical measures such as sediment dredging. However, with sediment dredging, it can be very costly depending on the size of the water body you have and how much sediment needs to be removed, whether it's contaminated, how far away you need to transport that sediment for disposal. Unfortunately, also with this method, once you take away the sediment layer, you can also expose a very rich phosphorus sediment layer as well. So then the problem still continues. You also have physical measures such as aeration, which is providing oxygen-rich water to the sediment water interface to prevent phosphorus release from iron and manganese-bound complexes. However, as soon as you switch that off, unfortunately, you can get anoxic conditions again, no oxygen, and then that will continue to release phosphorus from the sediment. So that's a continuous measure that would need to be in place. And as soon as you turn it off, your problem begins again. There are other measures such as chemical, with the addition of alum and iron salts. However, these come with different requirements of the water chemistry. For example, alum applications or polyaluminium chloride applications, the pH is important through application. Also, if you have a water body with a pH that goes above 8.5, you can also get phosphorus release from alum-bound phosphorus complexes in the sediment. Similarly for iron, you could have, if your water body does go anoxic in spring and summer months, any phosphate bound to the iron will then be released. And this is where I'd like to introduce Phoslock for those of you that don't know much about it. So Phoslock is a lanthanum-modified bentonite. It's produced through ion exchange, where sodium ions in bentonite clay is replaced with lanthanum. So lanthanum has a very strong affinity to bind with phosphate. So it comes in a granule form in the picture there. And then when we apply it to waters, we mix it with that lake water and apply it as a slurry. The slurry will then travel down through the water column and bind available phosphorus through the water column, and it will continue to bind any phosphorus that is released from the sediments. Through this binding of lanthanum with phosphate, it produces a very stable, inert, insoluble mineral called rhabdophane, and this is not the phosphate that is bound to this is not re-released under natural lake conditions. So a little bit more about it. As I said, it's applied as a slurry. The target of Phoslock is just phosphate. It can bind under a wide pH range from 5 to 9. However, it does outbind with that range, but the binding rate is just a little bit slower. So here are just some pros and cons of the main products used to treat internal loading in terms of chemicals. Phoslock is not a chemical, it's a geo-engineered product through the ion exchange process, as I mentioned. So here, I guess it's self-explanatory. The green is positive, the red is negative. So as I mentioned, Phoslock can be bound within a very wide pH range in comparison to alum and iron. It works under anoxic conditions. It doesn't affect the pH or the conductivity as it's applied. And it also has the ability to increase sediment stability. So if you have very fine or fluid sediments, Phoslock can help consolidate those sediments and potentially have then the environment to allow rooted aquatic plants to grow. And with that, you get stabilization of the sediment, which prevents sediment resuspension. You do not need to apply a buffer with Phoslock, as it doesn't change the pH, whereas things like alum and iron has the potential to do so, more specifically alum. Phosphate is also not released from Phoslock in the system when it's applied. However, it can be with alum and iron salts through alum with high pH and iron through anoxic conditions. The binding capacity also does not change. It doesn't age when it's in the system. Lanthanum within the Phoslock will remain there until it is bound with phosphate, and then it produces the mineral rhabdophane. So how do we calculate a dose? We look at how much total phosphorus concentrations is in the water column. We also can factor in any external loads that is known coming in. Also things like water birds, if there are a lot on your water body, we can calculate a load to include that in dosing as well. One of the primary target of Phoslock is to control the phosphorus release from the sediment. So we look at taking sediment cores and understanding how much phosphate is released from different phosphorus fractions within the sediment. And we do sequential phosphorus extraction procedure to do this. We look across the first three fractions, which is looking at loosely absorbed phosphorus, which can be released through benthic fish foraging, through wind and wave action. We look at how much phosphate is released from iron and manganese bound complexes through anoxia. And we also look at how much phosphate is released from organic matter in the sediment through high temperatures. We also take a number of different measures as well in calculating a dose, such as dry weight, density, sediment density, and other elements. So here's just a few pictures of the application. So this is a hopper, gravity-fed hopper. You would put the ton bags on the top of that, and then the granules are gravity-fed through to the bottom. And you can see there's a pipe at the bottom where the granules will then flow to the back and mix with lake water in this system at the back of the pontoon system. And then the mixed slurry will travel to around the back of the boat and be applied over the lake surface as a slurry, where it will then travel down through the water column and where it will reach the bed sediments. So there are a number of different application techniques that can be used, and this depends on the water body in question. We have had large-scale applications and small ones, and the system used will vary depending on that. We can also apply from land if access is restricted and things like that. We also use GPS to track where we've applied Phoslock, and this also can be tailored. So if you have deeper areas of a water body that has more phosphorus release, then we can control how much and where it's applied. This is just a few photos to show you what it looks like when it's been applied on top of the sediment surface. So on the left side of the screen, there is their sediment cores with sediment in the bottom and just lake water overlaying. And then there's an aquatic plant species in that one. So where it says 10 CL, no Phoslock has been applied to that. The next one along is 7 PL. You can see that this is immediately after Phoslock has been applied to the core. The next one along again, 7 PL, is 2 weeks after a Phoslock treatment. And you can see it's all settled down to the bottom, and the aquatic plant is actually growing more shoots as well. The middle photo is showing you how thick the application layer is. It's just millimeters thick. And the image on the right-hand side of the screen is looking at a bird's eye view of a container that has sediment and water overlaying. And then this is a photo taken 10 days after the application of Phoslock. Hopefully you'll be able to see in the bottom left-hand corner of that photo that there is aquatic plants that have been able to germinate through that layer, so it's not causing a physical barrier in any way. You can also see that benthic organisms have surfaced and then sort of tracked down, and you can see where they've tracked across the sediment. And benthic organisms will help to take that Phoslock deeper down into the sediment profile, and that's where Phoslock just remains. It remains part of the sediment profile. So now I'd like to move on to some case studies. The first one is looking at the Kralingse Plus in the Netherlands. This is our largest application to date. It's an artificial lake in the city of Rotterdam. It's a recreational water body heavily used by more than 3 million people a year. The lake has suffered with very poor water quality through external and internal influence. And the city of Rotterdam are struggling to find a solution in which they can use to comply with Water Framework Directive targets. And I'd like to just show you a short video now. This is the project manager at the time just discussing the sort of journey that they've taken using Phoslock.
So, welcome to Kralingse Plus. It is an artificial lake dug by hand from the 1600 onwards to produce peat for fuel for the city. 3.5 million visitors from the city and around the city are visiting its natural beauty, its wildlife, and are using it for recreation like swimming and sailing. We have a persistent water quality problem, which is related to too much phosphate in the shallow Lake Kralingse Plus. To combat that problem, we want to reduce the phosphate content of the water, which means that a reduction from the influx from the forest and the influx from the rivers that feed the lake. It is a complex of measures, and one of the most important one and the biggest one for the moment is that the bottom of the lake is also very rich of phosphate. We had an investigation, a broad investigation of all the possibilities to use to reduce the phosphate. We had the advice of engineering companies, universities, and of course our own knowledge as the Rotterdam. We made a scan of all the different options for solutions and for the binding of the phosphate in the lake, thanks to different water boards and universities, we stumbled upon Phoslock as a method. Then we did a market research all over Europe, the 28 countries of the European Union, whether or not they could provide us with an alternative. And nothing came out. We did an extensive research of 96 recent peer-reviewed scientific researches about the effect and side effects of Phoslock, both in the laboratory, in tests, in waters, and in lakes that were already treated with Phoslock. And it came out that there will be no negative effects. We invited a team of experts from science and water boards and water quality to give us advice and to make sure we were on the right track. That was very important to come to the right package of methods to solve the water quality problem and the use of Phoslock in this lake. With only a layer of about 3 millimeters on the lake bottom, the problem is solved. Phoslock is an excellent method to catch the phosphate that is released from the lake bottom. So it's simple as that.
Okay, so for the Kralingse Plus, they took a number of sediment cores. They took 10 sediment cores because the lake was split up into 42 zones, so 10 cores were taken in each zone. And then each of these 10 samples were homogenized to produce one composite sample. And then each of those 42 samples, a sequential phosphorus extraction procedure was performed to identify how much phosphate would be potentially released from the sediments under natural lake conditions. And because of that, we were able to tailor a dose based on each of these 42 sections. And you can see that the red numbers are the dosage in tons which was applied. This isn't a common method, so this is quite a, what's the word? It was quite an in-depth assessment of the sediment, but it just proves in these next slides the longevity potential of this, doing it this way. So these are results. So we have here a plot of total phosphorus and orthophosphate, and the blue horizontal, the dark blue horizontal vertical line, sorry, is showing you where Phoslock was applied. We're looking at 18 months pre and 18 months post-treatment. And we can see that the concentrations of both total phosphorus and orthophosphate significantly declined as a result of the Phoslock treatment. There are a few little elevated total phosphorus concentrations you can see in July 2022 and then again December and January 23. In July, this was when they were doing annual aquatic plant harvesting of the water body. And when you mechanically mow aquatic plants, they can release phosphorus into the water body. So this was a result of that. But as you can see from the orthophosphate concentrations, this didn't really increase. So Phoslock was working very well within its limitations here. And again, with the December-January increase, this was most likely from external catchment loading. And again, the orthophosphate concentrations still remain significantly low. And the box plots on the right-hand side there, just of before in pink and after treatment, you can see that they're both highly significant following the treatment. Moving on to Germany, this is the Behrendorfer in Germany. This is, again, a recreational water framework directive lake. It has a small catchment area and the runoff has been significantly reduced to this site. However, it did suffer from internal sources of phosphorus coming from the sediment, and the water column phosphorus was incredibly high prior to treatment, and the site had low aquatic plant growth. So a dosage of 214 tons was applied in 2009. And you can see from the bottom graphs, we have phosphate and total phosphorus. And we can see that the concentrations of both have significantly reduced since that one application, and have been significantly reduced up to 10 years post-treatment. The site has also seen increased macrophyte colonization depths and improved oxygen profiles. The site was monitored in 2019 for aquatic plants, and there were 12 new species that have been recorded, and 3 of these have very high conservation status. So it is an example of how the lake is recovering ecologically as a response to Phoslock as well, not also like chemically in terms of nutrients. Moving on to Bärensee, also in Germany, it's an artificial lake, a recreational water body with the biggest camping area in the Hessen state. So it's very popular with swimmers. Swimmers can provide 94 milligrams of phosphorus per day, so a huge amount of external sources, particularly if you have a high number of swimmers using the water body. It also still suffered from runoff and groundwater. Through assessment, the sediment was known to cause also problems in terms of phosphorus release, and the phosphorus concentrations were high prior to treatment. So 11.5 tons was initially applied in 2007, but as this is heavily used by swimmers, the water managers wanted to continue to see the benefits of the treatment and wanted to do periodic treatment top-ups to make sure that the water body still remained in a desirable state. And this is a good example of that. We have the Weizsee in Germany. This is an artificial excavation lake. It's a very important public lake in Weinheim. It's a commercial park, so people have to pay to enter and use it. It has a rural catchment and suffers from agricultural runoff, and again has a significant amount of swimmers, up to 35,000 a day. The site also suffered from internal loading from the sediments, and 94 tons of Phoslock was applied over 6 days. This is a good example of how Phoslock works well over time. The red arrow shows in 2015 where Phoslock was applied, and you can see that each year monitored thereafter shows even further declines in the total phosphorus concentrations. And this is because Phoslock can bind other compounds. It can bind to carbonate or to humic acids. However, these binding is weaker in comparison to phosphate, and the lanthanum in Phoslock has a preferential binding to phosphate, so it will displace those and preferably bind to phosphate. And I think this is what we're seeing in this lake over time, as we're seeing the reduced reductions, and I'll give you another example of that in a moment. So this is Lake Armo in Finland. It's a recreational water body. It's suffered from poor water quality as a result of phosphorus coming from the sediments. It's a low alkalinity humic lake. It was only applied, Phoslock was only applied to the southernmost area of the lake, which is the shallowest area. So 7 tons was applied to this water body in that area. So this is looking at the total phosphorus concentrations in the hyperlimnion of the water body, so the deepest area of the water body. And you can see the seasonal patterns prior to application. But if you look after the application of Phoslock, you can see significant reductions in the total phosphorus concentrations, particularly noticeable in the spring and summer, seasons. So when we look at the statistics, pre and post treatment, again, the box plots there showing before and after. The one on the left is looking throughout the water column. So as the water column as a whole, we've seen a significant reduction in total phosphorus. And again, in the hyperlimnium as well. We've seen an almost significant reduction in the epilimnium. I'll also explain why in a minute when we look at the phosphate data. So there's not as much phosphate data for this lake, but you can see since application, the concentrations again for particularly spring and summer are significantly lower since treatment. And again, when we look at the statistics, it shows that. Again, looking through the water column, we can see significant reduction as well as the hyperlimnium. And again, in the epilimium, we're not seeing a significant reduction, but this is most likely due to the fact the lake is still suffering from catchment loading, but also it was very low dose considering the size of the water body, and they only treated one area. So Phoslock is working within its limits in reducing what is coming from the sediment, but because of the low dose, it's not able to control those sort of surface water concentrations coming in from the catchment. This is Loch Flemington in Scotland, UK. It's a Water Framework Directive site. It's also a site of special scientific interest, so it has a number of protected species associated with it. Unfortunately, the site suffered from internal phosphorus loading and aquatic invasive species plants. Phoslock was applied in 2010 with 25 tonnes to this water body. Another good example of how Phoslock works really good over time, you can see the bottom table there in the left. You can see the Water Framework Directive target for this water body was 32 micrograms per litre of total phosphorus. Prior to the application, it was 60. 1 year after, it was 31, and then the second year after, it was 27. So it's declining over time. As thanks to the treatment, we had 2 new species gains to this site following the application. Also, macrophyte maximum growing depth increased, and also more characteristic species returned to a number of sampling points post-treatment. Unfortunately, there was an increase in the invasive aquatic plant species, but the authors of this paper, where these graphs come from, attribute this to the increased water clarity of the site. This is Heritage Loch in Scotland, near Glasgow. It's a recreational water body and suffered from poor water quality, both from the catchment and from internal loading. It's heavily used recreationally for water sports, and through lake assessment, we found how much was coming from the sediment, how much was in the water column, and how much was coming in from the catchment. This is another example where the number of water birds were known, and so we were able to factor in how much phosphorus was potentially coming from those, adding to the water body. So this site had 11.5 tonnes top up as well in 2022. And I've had good reports from the water manager that they remained open last year and are very happy with the treatment. So this is some of the data for this site. This is looking at total phosphorus. The red, blue and black lines show the water column concentrations, where the dark blue and orange show the concentrations coming in from inflows. So the vertical line shows where Phoslock was applied. As you can see, the Phoslock was able to reduce the phosphorus concentrations in the water body, but with the huge spike in inflows coming in from the catchment, you can see that there was an increase in the water body. However, this was only short and it was able to reduce over time. So this site quite clearly suffering from very high concentrations coming in from the catchment, but still Phoslock working to within its limits of the water body. Okay, so just to summarize overall, there was a paper published looking at 18 different types of lakes, looking at 2 years pre and 2 years post-treatment. And they reported significant reductions in total phosphorus and phosphate following the application of Phoslock. And this is just a good example of confirming the different Phoslock is very able and a versatile product to use across different lake types, whether that's high alkalinity, such as the Kralingsa Plus, or low alkalinity humic lakes, such as Lake Armo in Finland. So just moving on briefly to the ecotoxicity profile of Phoslock. For those of you that don't know much about the ecotox world, it's a completely different world, but I've put up a slide here just showing you some of the definitions of some of the dose descriptors that are used in ecotoxicology. I just want to focus on the EC50 dose, which is the medium effective concentration. So where 50% of test species that are tested show an effect. So effect endpoints vary. It could be immobilization or reduction in growth parameters, for example. So this is quite a busy slide, but I want to draw your attention to the very colourful plot on the right-hand side. This is looking at a number of different organisms, ranging from fish, zooplankton, bacteria, where Phoslock and other lanthanum salts have been used to understand their endpoints in terms of EC50 concentrations. So on the right-hand side of that plot, you'll see the endpoints that are reported as total lanthanum concentrations. And the red vertical line near the 0 on the x-axis shows where the maximum concentration of Phoslock in terms of total lanthanum has been applied to fresh waters. And as you can see from this, that it's very, very minimal in terms of what the endpoints are reported for these species, so where there is an impact of the lanthanum. And a lot of these species show a value of more than, which means that they actually haven't tested high enough to see and report endpoints for these species. So in summary of this plot, there is no risk to aquatic life because the concentrations that we see through a Phoslock treatment are nowhere near what is reported in the ecotoxicity studies. Just to confirm this even more in terms of human health, lanthanum is used in a medicine called Phosphorinol as lanthanum carbonate, and it's used to treat chronic kidney disease. So it's used for hyperphosphatemia, and based on the dosages, the daily dosages of between 1.5 and 3 grams of lanthanum per day, if we look at the nominal dose of 1.5 grams of lanthanum per day, in equivalent in terms of a Phoslock treatment, you would need to drink about 380 litres of Phoslock treated water per day to get that same elemental lanthanum concentration as a dose of Phosphorinol, which is just not doable. But even if you were to have this, there's patients that have been on this medicine for more than 10 years with no reported or negative impacts of treatment. So Phoslock is very safe to use and there is no threat to aquatic or human life. And there's been extensive research in this area as well to prove this. So just to conclude, we've seen reductions in both total phosphorus and soluble reactive phosphorus across different lake types, whether that's high alkalinity, low alkalinity, humic water bodies. We've seen rapid and permanent binding of phosphate to lanthanum and also long-term phosphorus removal, for example, of more than over 10 years. There's no ecotoxicological impact, and it's a very effective product to use. Particularly if you're using a one dose and you get a 10-year benefit of that dose, that's really significant in terms of cost saving for lake managers. So just wanted to end it there. Thank you very much for listening. I just thought we'd also mention briefly about a new product that we have called Phosflow. So Phosflow is for use in flowing water, whereas what we've presented on today, Phoslock, is for use in static water. But we're happy to answer any questions you may have arising with the new product too. Thank you.
Thank you, Damian and Kate, for this discussion where we have learned how Phoslock works and about case studies in the Netherlands, Germany, Finland, and the UK, where water quality was significantly improved as a result of treatment. Now it's time for questions. So we would like to ask you to please use the chat window in Zoom to send your questions, and we'll address them in a bit. Okay, so we're going to start with some questions that people from the audience have just sent. From Charles Hughes, And the question is a bit long, but maybe we'll try to shorten it a bit. Has PET undertaken Phoslock applications or studies of phosphorus mobility post-dredging? And basically, and he says, if so, how successful have these been following initial dredging of bed sediments, and how long would you wait before an application is undertaken once dredging has finished?
Yes, we have done some trials in Australia, actually, where dredging has occurred and then Phoslock has been applied. But I think this is still ongoing, so we're not too sure of the results just yet. But I believe from initial results, it's looking incredibly positive. I think you would apply it as soon as you've dredged it, because I think you would have the sediment, you potentially have a sediment-rich phosphorus layer as soon as it's exposed. So you would apply Phoslock as soon as you've dredged.
Yeah, we've also done a lake in the Netherlands to make sure that the effects of Phoslock would be long-lasting, and it was actually the project that led on to the Koningsplas, where we actually dredged a section of the Blijksvaartsum. And as Kate mentioned, it was straight afterwards, so that you actually capture any nutrients that have been released from that disturbance, but also to sort of make sure that you're not allowing anything to sort of creep back up into the sort of water column. And that allowed that water body to stay open. Again, it was a recreational lake. There was a lot of sort of negative PR on the sort of local authority to create a solution to enable it to be used. And because of the success of that and combining a dredge and then a ply soon after, it worked very well and led to the Koningsplas that Kate demonstrated as a successful and continuing to be successful case study. But I can share any additional information with Charles. I'll pick up the contact details and I will respond to you.
Okay, thank you. So let's go on to another question. Mohamed Suleiman asks, what kind of lake modeling is used to test total phosphorus and orthophosphate, and whether Phoslock is safe for lake ecosystems?
So in terms of modeling, there are a number of different modeling systems that can be used. But generally, I mean, we look at getting actual data. I mean, if you get actual data, you can put that into modeling programs, but we need to look at the seasonality as well, because the phosphorus concentrations do change throughout the season. So you need to look at an average usually across those seasons, and then that helps with dosing. But modeling can help and can be used for Phoslock treatment. There wouldn't be a problem with that. It really depends on the end goal of what you would like to do, and each lake is different, and so we would assess each lake individually. As Phoslock is used specifically for targeting the phosphorus coming released from the sediment, then that's obviously, depending on the size of the water body you have, that's something that would need to be factored in as well. In terms of the ecological impact to the system, I tried to demonstrate that there at the end, but there's been a number of studies looking at aquatic plants post-treatment, and many of them have increased in their coverage, or as I demonstrated with a few of the case studies, we've had actual endangered species come back following Phoslock treatment. So there's no sort of negative impacts associated with that. The Phoslock can bioaccumulate in particular species, but again, we've had no negative reported impacts as a result of the Phoslock treatment in those bioaccumulation studies.
Okay, thank you, Kate. You were mentioning, I think you mentioned the timing of Phoslock, or no, how you mentioned how phosphorus can vary throughout the year, and so there was a question about when is Phoslock usually applied?
Yeah, so typically we apply during autumn through early spring. And this is because the majority of the phosphate that is in the system will be in the sediment. So when all the breakdown happens from algae and aquatic plants from the summer, as they break down, the phosphorus comes out of them and will return to the sediment. So the optimal time to apply Phoslock would be within that window when you're targeting the sediment. It can be used out with that window, but then it comes with risks of longevity of the treatment, for example. So there are pros and cons to both, but optimally you will apply it in autumn through early spring.
Okay, thank you. And how long does it take for Phoslock to clear out of the water column after it is applied?
Yes, so this depends on the chemistry of the water body. Usually 90% of the phosphate in the water column is bound within the first 3 hours of it being applied. In higher alkalinity waters, it will take a little bit longer to settle out of the water body, but generally very quickly, if not hours to days, depending on the chemistry.
Okay, thanks. So moving on to something else, we've had some questions about the cost. One is very specific about euros per kilogram of phosphorus binded, but maybe you can speak to us about costs in general or as specifically as you wish to, of course.
Yep. So no, cost from conversations that we've had with clients, both past and current, Phoslock is not an expensive solution because it is effective, and we can identify that. So when we have a look on the return on investment, it's clear it was the right choice that was made. Each lake is different. It depends what each client is looking for. Some clients just want to push themselves through the potential spring-summer period where they get the nutrient levels high and it causes them issues. Others want to have a bit more of a long sort of term solution where they're looking to sort of treat not just the top 2 or 3 centimeters, but the sort of top 5 and might even go down to sort of 10. But again, price is dependent on what the client is looking for. As we say to everybody, it's if you've got the data and you have lakes and you want us to understand the benefits of using Phoslock, we can provide costs. Again, it's about application, it's about operation, it's about location. But when we actually do get around the table and we have those commercial discussions, we don't normally leave without an order. So I would just sort of say, please reach out, let us know what your challenges are, where your lakes are, and we will do the data crunching and we will be able to provide quotes. We've got a lot of information. We've done 300 lakes. We've been going for 20 years. So we can actually turn it around very quickly and engage to make sure that there is an understanding, there is a volume, we can agree commercials, and then we can actually apply end of summer through autumn, winter into the sort of springtime to make sure that waters are healthy and ready for an ever-changing climate.
Okay, thank you, Damian. We also have a couple of questions about the possibility of using Phoslock for phosphorus removal in wastewater treatment plants.
Yes, it does have the potential. Obviously, the new product we have, Phosflow, is probably more suited to wastewater treatment works as it's flowing water. With Phoslock, if you applied it as a sort of final polisher at the end of your wastewater treatment process, it's about being able to, as Phoslock breaks down into very, very fine particles, it's about being able to keep that within the system so that it can be used to bind the phosphate. So I think Phosflow would probably be more suitable, as it's pelletized. It doesn't sort of break down into very many small particles. It stays as it is, and it's specifically used for flowing water. So happy to discuss further if those people with those questions would like to, in terms of the Phosflow.
Okay, thank you very much.
We also, sorry, Christine, it's a good question. We also do have some inquiries where people are able to hold on to the wastewater once it's gone through a process treatment before it's discharged out. And in those locations or those applications, we're able to treat with Phosflow, but also if it's contained, then we can apply Phoslock onto that water, treat it as a column, allow it, as Kate sort of said, 90% within 3 hours, and then allow it to be sort of discharged. So the technologies Phoslock and Phosflow can apply to different environments, and we're really excited to see where people are looking to push and test and use this outside of its original lake water sediment. So all those sort of questions, please send across to Kate or myself, and we'd be more than happy to look at answering those.
Okay, thank you. Since it's going to be 2 p.m., I think we might want to bring the session to a close. So if you and our speakers will be able to get in touch with you if you left your questions in the chat window, and also please go ahead and contact them for any further questions you may have. We have their contact information. And I would like to thank our speakers for this interesting discussion, and also to everyone that has attended the event. You're going to see a brief survey on your screen now about the topic of this webinar, and also to see whether you would like to be contacted with further information. And also, I would like to remind you that you will be able to watch a recording of the event in the website of Smart Water Magazine.